Looks like we're picking up some attendance and it looks like the recording has started. So welcome. My name is Andrew Young. I'm here today with Shane Cannon and Samir Shende, and we're going to give you a quick tutorial on containers and how to get started in the context of HPC. So this is meant to be, let me see if I can, a pretty quick tutorial. If you haven't, you should go to that link right there. If actually, Samir, if you want to copy and paste that into the chat, that would also be useful. We're basically going to run from that today after some intro slides from me, but here's basically the outline. We're going to try and keep this fairly introductory. We figure most of the folks here are probably fairly new to containers and looking to have sort of a quick one-on-one of, you know, how to use containers. How does this work in the context of HPC? And so we're hoping to give some hands-on experience real quick. So I'll introduce containers from the conceptual standpoint, how they relate to HPC. Shane's going to talk a little bit about, and show you how to build your first Docker container. If this is your first Docker container, maybe it's not. We've got some Amazon EC2 resources to work with. And then we're going to try and deploy a couple of things quickly on a supercomputer at NERSC. So. And then from there, we're going to ramp up quickly. We're going to have Samir share some of what he's been doing with E4S and how that plays with containers. And so that'll be a quick preview into some of the more in-depth things you can do with containers, and really with a special and particular focus on not only just HPC, but really DOE exascale machines as a whole. So. And then we'll try to wrap up very quickly if we have some time with some best practices. It's also worth stating that this is a very small hour-and-a-half tutorial of what we have essentially done several times now at both ISC and SC conference series for including full-day tutorials. So, consider this the tip of the iceberg, if you will. We have a lot more training materials available, which you can reference if you're interested. So we can point some links towards the end. You could actually rerun through the entire SC21 tutorial that we have. So that should be, basically a quick way to really ramp up if this is something you'd like. So I'm going to give you a quick intro here, fairly quick. Again, I think we can be fairly flexible. It's Friday afternoon. If somebody wants to interject, pop in, have a comment, a question throughout this, I think, please feel free to do so. So we'll keep it fairly dynamic here. So let me start you off and just try to let's cover some basics. What is a container, right? What are we doing here? What are we talking about? So essentially, containers represent this lightweight execution mechanism of running packaging and running an entire software stack and trying to encapsulate everything that we need to run a particular process, task, etc. By everything, we mean almost everything. We're not including the OS kernel, for instance. And this basically limits us to many operating systems, so long as you choose a Linux operating system, which isn't really much of a choice if you think about it. But essentially, a lot of the container foundations are really built around Linux today, is the point here. These are essentially still run as processes, and all the user level software is essentially isolated in a quote unquote container. And you could think of this as a way to create a portable, with some asterisks, right, software ecosystem. A lot of people talk about containers in the same context of virtual machines. I'm back and forth on this. I like to, if you're familiar with it from a Linux perspective, think of it rather as change root or chroot on steroids rather than a virtual machine. This is OS level virtualization, if you will, rather than ISA level or hardware level virtualization, although some of those start to bleed in, especially when we're accessing peripheral devices. But many of you are probably familiar with virtual machines. Think of this more as chroot and notice that it is different. If you've heard of containers and you've used containers, you probably also have heard of and are familiar with Docker. It has been the most common. I would say this use case, Docker is declining rapidly. Through broader perspectives in the industry. There's been a lot of shifts, but Docker's still the thing you're probably going to touch first on, say, your laptop as you start to experiment with containers. It's widely available. It's used in industry, and again, that's actually changing under the hoods now, even though you may not realize it. And it's well integrated with really their Docker hub, as well as any other container registry service that you may run into nowadays. So you've probably heard of Docker in this context, right? So what do I mean about containers, right? So this is actually dependent on the host level kernel, where we have a runtime that is part of the operating system or on top of the operating system, if you will, using key aspects of the Linux kernel itself to present a containerized, isolated environment that has, everything you need to start up a task, right? This includes full Linux distros, libraries, compilers, if you put them in there, whatever data you put in there, et cetera, as well as potentially other separate libraries that you may bring in from the host system as well, as that's obviously possible. So just a quick view, we're not talking about running, this is up and on top and leveraging the Linux kernel rather than alongside as you would see in a virtual machine. So a little bit different context here. So containers are used pretty extensively today in the cloud industry. Oftentimes these are used to represent microservices, where maybe I have a comprehensive set of services I need to deploy, and I can break them up into quote unquote microservices. Some, web service containers, a database or two, a log container, and then a load balancer to balance that load across the different Apache servers and an ingress server as well. And then these microservices are orchestrated in a way to represent a fundamental service deployment, right, that can be scaled up and scaled down from there. And a lot of times what the cloud industry or hyperscalers are trying to do is jam as many containers on hosts really for increased system utilization, and then trying to figure out how to scale the size from there. A lot of folks have been really interested in sort of the DevOps aspects of containers, right? You're going to see a little bit more of this, but I get to really have a method to synchronize my development environment from a deployment environment from my test environment, right? And only the changes are really pushed into production, not a whole brand new giant virtual machine, through the way in which we leverage layers in the OCI standard. So the idea here is maybe, you develop on a laptop and push to some production service or cloud resource, right? Interact with GitHub and other registries, repositories in a similar fashion that many folks are familiar with Git, for instance. That being said, there's some use in the context of HPC. We really need to do a better job at supporting our emerging software stacks, be it ML, DL frameworks, for instance, or other novel computing architectures that are being often targeted towards our leadership class HPC resources. And a lot of this, also relates, we see a heavy need for bringing in and leveraging some of the similar DevOps practices that you see in industry into HPC, right? There's an ability to support new frameworks or, even platform services. That being said, well, that all sounds great, and we'd love to leverage this today. In some cases we do, but it's worth noting fundamentally HPC systems are very dissimilar from a traditional cloud infrastructure, right? Instead of processing one or a set of services, say 1 million times a second, we're interested in one very big problem that gets broken in maybe into 1 million different subtasks, right? Through bulk synchronous parallel workloads. And we really focus on scale out based architectures. HPC has performance in it in the name from the get-go. Performance is paramount. So whatever we utilize in the context of containers, we need to make sure that it is still performant and with minimal overhead. So what do we really want in the context of HPC? Well, we have this BYOE, right? Or bring your own environment. I want to be able to build a container image that I care about, go and move that to an HPC resource and run it, right? I want to have composability as a fundamental aspect. I can define, as a developer, exactly how I want my software environment to work, exactly how to build it, and then just hand it off, right? And potentially have some notion of reproducibility on the way, right? And I just said, hand it off. This notion of portability, that I can go and build and run my software ecosystem, say on my laptop here, but then go deploy it on an HPC resource or a cloud resource or whatever have you, right? This notion of portability is fundamental really to the advent of containers. So, and as I mentioned, we really want this DevOps-based infrastructure, version control, and how that integrates well. Leveraging the ability to build off multiple layers and control all this in a, simply a very simple Git-like manner. So as you can imagine, there's a lot of things we're just not going to have in the context of containers and HPC, right? Overhead is first and foremost. Can't have that. We've done a lot of work in research, in identifying, searching, and eliminating areas of overhead as much as we possibly can, right? And I think we've got some good lessons learned to share with you. Containers today can be absolutely just as performance as installing in a native setting. We don't really care about microservices. That's changing. There are some, front-end science gateways that we're seeing, and there's some emerging research in this area. But for the context of this immediate meeting, we're not focused on microservices or on node partitioning. The idea is I'm probably going to run one container or identical containers that can fight amongst each other for resources on one node. And we can't really have root level operation, right? Or commodity networking. We run these systems in a fundamentally different way. So Docker doesn't really fit. There's some fundamental security issues. I can't just go load Docker on a shared HPC resource and give everybody root for obvious reasons therein. But there's some other integration issues as well. The good news is we have many different container options for HPC. There's 3 that you'll find across the DOE today. Shifter, Singularity, and Charliecloud. There's some new activities ongoing with Podman as well, which maybe we'll touch into in a little bit. But these are common, I would say you can find these on any major HPC resource, at least in the DOE, if not a lot of other US-based systems in the past couple of years here. So, and they all work fairly well. I think that's an important thing to take away, right? Without getting into too many details, they all take different routes and approaches, but these tools have been very successful in running containers and running them at scale, right? So what we really want to do is support this notion that we can build and test on laptops or workstations, develop, their container images, and then, have some specificity to that, and then go and deploy on a larger resource. To do that well, we really need to focus on interoperability and focusing on standard container images as much as possible without losing this notion that performance really fundamentally matters for us. So how this all relates to the tutorial? Well, there's a quick intro, very quick and dirty intro to what is a container. We're going to now turn it over to Shane here in a minute, and he's going to show you how to build your first Docker container, or what you may think is a Docker container, and then how to go and run that with Shifter on a NERSC resource. So we also really want to give folks exposure to E4S as much as possible. While you can go and build E4S natively, we are offering container images and a lot of customization across multiple different target architectures and platforms with E4S in a containerized manner. So Samir will share that and some of his experiences and details there. And then I think we can go back and cover some of our best practices and hopefully leave you with some interesting food for thought and ways to proceed forward if this is of interest. So let me stop there. Again, here's the link if that isn't in the chat or you haven't seen it yet. Looks like Samir's got it in the chat. Thank you, Samir. Feel free to go to this page and start following along. You'll find a link exactly to these slides, but we're going to transition next to Shane here and start with module 2. So Shane, if you're there, I'm going to stop sharing and turn it on over.
Okay. And maybe just a few things before we jump into it. So first off, if you haven't already, and it looks like many have not, go into the Google Doc link from the website that was posted there and make sure to claim an instance for the tutorial activities we're going to be doing. So let me give people a minute or two to do that. I'm going to bring up that page myself. Hold on just a sec.
I will put it in the chat right now.
Yeah, do that too, just so people can go directly to it. Just claim an instance, and then the instructions for how to connect to it are up above. I'll be connecting via SSH, but if you don't have an SSH client on your system or something, you can also use this this other login method that's shown there. I think for Samir's portion, he might use that a little bit more. Okay, and so people start claiming your instances. In the meantime, I'll go ahead and bring up my screen, start sharing. But maybe just one other thing before I do that. Some of the first portion is going to be somewhat introductory. I was wondering, could we just use the reaction button and do like, you know, a hand raise or a thumbs up or something like that? First question I wanted to ask is how many people are already familiar with Docker and maybe use it occasionally for things HPC or otherwise?
Good. We got several.
Okay, so there's few out there. Yeah, it's hard to get a good. I wish we had the poll stuff enabled so we could try that. And then maybe just so I can easily differentiate it, maybe do one of the other emojis, the fanfare or something like that, if you have never done anything with containers. So this really is your very first exposure to it. Andrew. Okay, a few, but not too many. Okay, well that's good. You know, I'll probably go through this first part a little bit quick just because it is introductory, but I'll try not to just breeze through it completely. Right. So now I'm going to try to.
So Shane, as you work on getting your screen sharing here, I guess I want to introduce this image a little bit first. We've gone ahead and prepared an EC2 image that we can actually share with you. That obviously we've also booted up several of these as well. And the advantage here is we've done some of the hard work for you in terms of installing and configuring various container runtimes. So it's a good way to just, you don't have to install anything. You can use these EC2 instances. They will be just, we will power them off as soon as the tutorial's over, but we can share the AMI. But really here, we're just trying to make it easy for folks to not have to install anything, but still get some quick experience. So looks like Shane, you've got everything sharing. So
yeah, are you seeing, what are you seeing right now?
We're seeing the list of your current container images.
Okay, and the web page too?
No, just your shell.
All right, let me try seeing if I can get it to show what I want it to show. I've done it before, but now I'm going to have trouble. Let's see. Yeah, it might not let me do it quite the way I want. Okay, well, I'll just, I was trying to do a split screen so I could show the instructions too, but I'll keep it my view this way so that I can reference it. All right, so hopefully people are connected in. We're going to start off with just some basics of, how to use Docker to pull an image down, run it, and then we're going to go through the steps of what it's to build your own image. All right, so I'm logged into the tutorial. I'm going to change my prompt to slightly different, just so I've got a little more space to work with. All right, so first off, there've already been a lot of images pulled on these, so you will see things. If you list things, you'll see a lot already. But we're going to start with just pulling down an image and like this. And you'll see what it's going to do is it's pulling down sort of the layers that are needed for this image, which we can then use to start a container. Okay. So this one here, we're pulling Ubuntu 18.04. What happened there is it went to a registry that, in this case, it's a public registry that's run by Docker. It's one of the more standard ones that people use. And it pulled down, this reference Ubuntu 18.04 image. so that's good. If you can use the Docker images, it's not shown in the walkthrough, but you can use the Docker images to list it. Now you'll see a lot of images here because we've pulled a lot of different things, but I can grep for Ubuntu and you'll see this is the one that I just pulled. So next, let's try going into that image. Fortunately, like the little button is right in the way. Hold on, let me try moving it. Okay, there, that's better. All right. All right, and I'm going to use a couple of flags here. The -it means I'm going to use Docker run to run a container. The -it means interactive in a pseudo terminal. So you could not pass those options, but then you would the interactive experience wouldn't quite be what you would like. And I'm going to do the Ubuntu 18.04 image name that we just specified before. All right. So here we are, we're in a container. You can kind of tell that something happened because the prompt changed. A few things to notice right off the bat. One is there's this, your root. This is a kind of standard behavior in a lot of containers. You know, they'll just put you into the root mode by default. And that just means you're root in the container. So it doesn't necessarily mean you have any extra privileges on the host necessarily, but you definitely do within the container. And then the other thing is we can do cat etc os release and we'll see, yeah, it's an Ubuntu release 18.04. And just for your information, the system we're running on is using like an Amazon Linux distro. So, you know, this is clearly a different environment than what the host system has. All right, and next, and so that was us being in a container. We're going to exit out. If you're trying to run Docker commands and you're seeing like command not found, you're probably still inside a container. You just need to exit out. So for example, if I'm in here and I do Docker, it'll say it's not found. So just if you're trying to do the next step, just remember to exit out. Okay, that was a load of fun, but that's us just using images that somebody else has already created. What if we want to kind of create our own? So let's start that process. We're going to start by just making a kind of a working directory to do this, and it already exists because I think we had set this up before. So you can just change into it. If you want to do it from whole cloth, you can try, you know, making a different directory name and then changing into it. In this case, we've already got the contents for the demonstration we're going to use. So first we've got a script called hello. It's just a bash script that does an echo. And this is one I'd already modified. If you want to customize it, you could, you know, you just edit that and, you know, change it to whatever. All right. And then the second thing we have is a Docker file. So the Docker file is a recipe that is used to construct an image, and it just uses a couple of a small set of kind of command, you know, verb kind of commands that you use to either tell it stuff about your image or have it kind of manipulate the image that you're creating. So I'm just going to quickly walk through these. So the first one is from. This basically is like, what are you going to start from? And so in most cases, you don't start from like a completely empty space or tree. You start from some, you know, either a distro like this, or you might start from a language one like Python, or you might start, if you're doing a service, you might start with, you know, Nginx or some other thing, and maybe you're going to tweak it a little bit or something like that. But the nice thing here is you could create new base images and share those and then use those to layer apps on top of. And when Samir shows some of the E4S images, you know, you can kind of think of those as that way. Those are kind of a starting point for building other application images. Next is this label. This is just a way to put metadata on the image. It's a free-form thing. You could put anything in here, but one convention is to put the maintainer in. So it's always good practice just to at least put this one in, but you can also put other attributes if you want to, just as key value pairs in the metadata of the image. And then now we get into the more interesting thing. So one is like, when you're building these images, basically what it does is it kind of starts up a container, and then you're doing operations inside that container, and then it sort of saves the final state of that as a name. So we'll see that in just a bit. So there's kind of two different things that you typically need to do. One is you want to inject things into the container. You want to bring stuff from the outside in, and that's what add or copy is used to do. So here we're saying, take the hello in the place where I'm building this and place it in bin hello. So that's one common thing. The next is run, which basically says like, do whatever command is on this after the run, do that inside the container. So you're basically kind of, you're manipulating things inside of there. So in this case, I'm just changing the permissions on this file, but you could do things like go curl, download, do a get checkout. You could build, do a set of build steps. You can, install other packages. All of those things would typically be done using run. All right. So again, very simple example, but enough to kind of give you the idea of how these things work. Now let's build it into an image. So to do that, we're going to use Docker build. We need to give it, we can build it without it, but we'd like to have some name so that we can reference this. So we're going to put -t for tag, and I'm going to call it, there might already be one of these in there, but I'm going to call it hello 1.0. And it's easy to overlook in the web page here, but there's a dot there, and that just means do it in the local directory. You could actually say build from a different path if you wanted to. All right, so we're going through and it's doing it, and you'll kind of notice that for each of the kind of verbs that I had in my Docker file, it does a step for that. So, it shows that it's building, it's bringing in that base image, it's adding this metadata, it's adding the file from outside, and it's running it. It's doing that run command, and finally it does a commit to kind of create that tagged version. So now if I do a Docker images and grep hello, I'll see that one that I just created right here. All right, and just to show that this all worked, let's now run this. We'll start by running it interactively like we did earlier with the Ubuntu one. And we're placed in here, and now we can run hello, and you can see it there. And because I put it in the bin directory, it's already on the path. So I don't even have to, give it any, I don't have to do, bin hello. I can just type hello since it's on the path. The other thing to know is you don't have to interactively run it. You can just run these things from outside as well. So you can do something like this. Again, since it's on the path, you can do that as well. All right, so, that's walked through the basics of how to build an image, how to use a Docker file to start building up images. This right now is just within this instance. There's no way for others to kind of see it and reuse it. And so the next thing you may want to do is push it to a registry. Now, I'm not going to do this in this case, just partly for time, but also because it means logging in, and I'd have to put my credentials in. Keep in mind, these are accessible. We're using the same account and password for all of these. So you may not want to do the next step in these instances. It might be a better thing to try on your own laptop or other system later on. But if you want to explore this, you can. But you can go to Docker Hub. You can create an account there, just like you would for GitHub, for example. And then they'll allow you to push public images to that registry. And so the steps that you would do are, first, you have to retag your image because it needs to go into a namespace that you would have control over. So for example, for me, I'm scanning on Docker Hub, and I would do something like this. The next step I would do is I would do a login, and it'll prompt me, and I would do scanning, and then I would put in the password. And then after I've done that, I could do Docker push scanning hello 1.0. After doing that, you can actually go to the Docker Hub site, navigate to your page, and you should see that image showing up on the website as well. And then, of course, the real magic is then you could go to some other location and pull that image down, even if you hadn't built the image on that system. So that's a quick walkthrough of, running images, building images. We've got a hands-on activity. If you want to, let's give people, how are we doing on time? Andrew and Samir, we're doing okay?
I think you're doing just fine. Yeah.
Okay. All right, good. Let's give folks maybe 5 minutes or so. If people want a little extra time, just make a comment in chat and we can extend it. But try going through the hands-on activity. I tried to hide the answers, but it didn't quite let me do it in this template we're using. So if you can, try to not scroll down too far and then just do the MPI Hello World activity. A few hints, there's the code that you can run in case you're not an MPI programmer is right there for you. So you can just put that into a file where you're going to do your builds, just cut and paste it. And there's a few hints. We're referencing an image that we've built before in the past that already has MPI installed in it. And there's a hint on how to compile the application as well. So between doing the Docker file add and run, you should be able to get this application compiled. I did want to point out, in this case, I used a kind of a reference MPI image that I had built before. Samir has an example of doing this with E4S. And so we'll try to paste an example of that as well. The only reason I didn't use it here is a little more complicated because you have to do some things to initialize the SPAC environment inside that image. So I decided to just stick with this one for now. But as you do more complex things, especially if you want to use some of the E4S tools, I think you definitely want to look at that approach instead. So again, give you a few more minutes. Hopefully people are already working on it. In the meantime, I'm going to see if there's any questions that have come up. Also, if people want to, raise their hand or just unmute and ask a question, we can do that now while people work through the activity. And maybe, I think the answer for this problem is already in the directory somewhere. I'm going to look and see.
And if you're looking for the image for MPI, it is in CD to the SRC demo containers directory.
Oh, it's capital.
There's a hello MPI folder.
And the CD to containers. There it is. And README file has that.
Yeah. So this is an example that I was saying where you can use the sort of an E4S based image. This was the part that's a little extra bit of work that you have to do to initialize the environment. So if you want to, you can try it with the example that I provided, but you can also try doing it with this. And again, that's already in the boot image that we have on these. So you should be able to just navigate to there to see that as well. I'll quickly do the one that uses just the slightly more simple one just for reference. Actually, let me. And by the way, the page was adding this little extra character, and I apologize. I tried to get it to disappear, but I couldn't. So delete that little greater than symbol that's in there.
There's also hints at the very bottom.
Yeah, definitely take advantage of the hints. So I'm gonna, in this case, I'm gonna use this image just for starters, and then we might show how you change it to use the one from E4S. All right, so I'm just kind of doing it myself just to get an idea of timing. Hopefully people have had a chance to go through it. Let me finish letting it build. Why it's taking so long. One thing to know is notice how we made a directory and we did things in that. Part of the reason, I thought I'd updated this, but I guess this one doesn't have it. Part of the reason you want to do that is when you do the build, it'll kind of package, it kind of snapshots everything in that local directory. So it sort of can track the state of it. And so if you're in a directory that has a lot of stuff in it, that process will be really slow. So generally you want to kind of make a working directory for these things, or a lot of times you'll just have the Docker file as part of, you know, in the top level of a, say a GitHub, a Git repo. All right, so it is, oh, we got a, is it getting hits? What is that?
In the hello world.c, there is probably a last line that you need to delete.
Okay. Oh, that's what it is. Yeah. Thank you.
That hints.
Yeah. And it's the reason I didn't see it is because it's my toolbar is right over it. Okay. That's fine. I could also add a line to avoid that error message too, that warning. Okay. So now that we have it built, we can try running this image real quick. And hello. So we're gonna do it that way. We can also do, you know, something like this. Now this is all just running inside this AWS instance. So it's not like suddenly I've made a supercomputer in a container or something. It's still just going to be limited to the CPU resources on this one node. But this is just to illustrate that you can kind of go through the process and do basic testing, you know, even inside this container. And then a little bit later, we're going to show how we can run sort of the same image in a real HPC system. All right, so that is the walkthrough. I'm going to start into the next module, but maybe a few things before I do that. One is just surprise, actually we're using Podman for all of these activities. So even though you can type Docker, in this case, Docker is pretty much just an alias. I can't remember if it's an alias or a wrapper. Yeah, I think it's a wrapper script, and it's actually using Podman underneath the hood. Podman is a drop-in replacement for Docker, and it's got some nice features because it's really been designed to run without any privileges or very reduced privileges. And so that makes it an interesting alternative. It's being actively developed by the community. And so we sort of see this as being, you know, a future replacement. We are even at NERSC looking at it as a potential option as an HPC runtime. So that's it on the basic ones. Before we pivot to the next module, if there's any questions, feel free to unmute and ask them. All right, so no questions so far. I realize probably a lot of you are already familiar with this, so this is probably just kind of a rehash. So, all right, we're going to go to the next module. Okay, now you can do these activities on the AWS instance because we have Shifter installed here. That's what we're going to be using for this next module. But if you want to try it on Corey, we've got training accounts set up. Let me repaste the link. The link to the sign up, the place to get the account is in the GitHub site. And then let me repaste the code that you'll use to request the training account. I'm just going to put it in chat here.
I can do that again. Oh, so you got it.
Got it. All right. So in these training accounts, I think they're active through the rest of the day. So if you're not able to, if you're still in the process of getting set up and stuff like that, feel free to log in later afterwards and try going through these steps if you want to. All right. So I'm going to go ahead and log into Corey. I'm just going to do these using my normal regular account. Also, for any of you that are already NERSC users, yeah, you can do these. We don't have any reservations or anything like that set up for this. So you can just use your normal account. And I just would suggest doing an interactive session to try these out. So so now we're going to start into, using Shifter to run containers on a HPC system. Just to note, like a lot of sites might be running Singularity or Charliecloud, one of the other runtimes. The commands are obviously going to be different, but the general flow of things is going to be very similar. So hopefully you'll kind of get enough of the context here that you could try it on another one that has a different runtime and you could figure it out. So we're going to start by pulling an image down just like we did before. Now, instead of doing Docker pull, we're going to do a Shifter image pull. And Shifter has kind of two commands. There's the Shifter IMG that's for kind of image related things, and there's just Shifter for doing the execution. So I'm going to pull it down. Usually this would already have been cached and you would see like it would be super fast and it would just immediately be ready. In this case, I guess it's been a while since it was pulled and maybe something's changed. Okay, so now it's pulled, and just like with Docker, I can use the Shifter command and to run this image, and I'll do that. And kind of like before, it's a little hard to tell. So one thing to note about Shifter and some of the other HPC runtimes work the same way is you'll still be yourself. You won't be root like you are in Docker. And so this is partly for security reasons, but also to make it a little more of a natural experience, because now I still have access to my home directory. I still have access to my Scratch directory, just like I normally would. The only difference is if I look at OS release, you'll see it's Ubuntu 18.04, just like we saw in the Docker system. And for those that aren't familiar with Corey or some of the craze, they generally run a /OS. So if I'm outside the container, so I'll exit slowly. I think I can do the same thing. Boy, I don't know why it's taking so long to exit out. It's odd. I'm gonna just start a new session just because I'm not that patient. Could be Corey's just having a senior moment. No, this could be bad. I don't know if it's just this login node. Let me try going to a different one just in case that's what's going on here. Oh, and sure enough, the others recovered too. Okay, so let me I'll just pick up over on this one. All right. We can also, but I was going to say you can do this, and there you can see that /. So that's the native OS. There's a question, do you have access to hardware performance counters? In general, yes, there's sometimes some special things you may need to do to get access to some of the pieces. We've got on the NERSC side, I think we do have some documentation about how to run some of the performance tools inside the container. In general, they just will work, but the one thing that could be tricky is to keep in mind, like the performance tools may not be in your image and not in your container environment, so you might have to like access them a slightly different way. You should get native access to the hardware as terms of like the interconnects and stuff like that as well. All right, so now let's try doing, that was on a login node. You can also do the same thing on a compute node. So we're going to do that here. Let me just cut and paste this actually. I'm just going to use the interactive queue. That's generally fast enough to get pretty quick turnaround. And you'll notice that in this case, I passed the image name as part of the salloc. You can also do the same thing in a batch script, which we'll show a little bit later. When you do that, Shifter at least has some integration with Slurm, and it'll actually kind of pre-create the container environment for you. So I can do something like just Shifter bash, and it, because I specified as part of the allocation, it'll just drop me in there automatically. And you can see that that was pretty fast. This is the way we recommend it if you're trying to run MPI applications. Okay, so I'm now out of the container, but still on that node. Maybe there's an example in the docs of how to do a batch script. I'm going to skip that just because it'll probably take a little while to run. But if you want to try some of that later on, you can look in at the instructions. The important thing to notice here is when we did the srun, we're doing we do srun and Shifter. So it's almost like any kind of srun MPI application that you would do. The only difference is like you have Shifter sort of sitting in the middle. All right. Next, we're going to try running a parallel job. So we're actually going to take the Hello MPI one that we did earlier. Now, I would suggest not bothering with pushing the image and pulling it down. If you really want to on your, later on and try that, you can. In this case, I think I've pulled down some versions of these before, and I'm gonna try running one of those. Oh, yeah, you can see lots of people have done this. So we can see everybody that's done tutorials in the past. All right, so we're gonna take, I think either one of these will work. Let me try this one. I apologize. I should have tested this out earlier, but I'm just kind of reusing things that we've done in the past. Okay, so like before, I'm going to do an salloc. I'm going to grab that image, and that should be good. And so we're just going to do 2 nodes in this case. All right. And first off, let's just, well, I'm just going to do exactly like how it's written in the instructions. You'll notice this next part. This is a little bit of it's documented on the nurse site, but it's something you wouldn't know obviously off the top of your head. Because this image is a little bit older, it has an older OS release with an older glibc. The way we do the MPI support is there's some dependencies that kind of get picked up in here. By specifying this module, it'll force it to use kind of an older snapshot of the MPI libraries that we inject into the image for running this job. And I'm going to explain what I mean by all this, but first I wanted to give some short explanation for that. Oh, that's interesting. Yeah, I should have, I've left off a critical piece here. Can't follow my own instructions. Yes, I really should have run through these earlier. I think I'm getting bitten by some recent upgrades, and I'd forgotten that these were going to happen. My apologies. I'm going to update the instructions to include an image that I know will work. Let me just quickly try this real quick. This one might behave better. I think we're getting bit by, they did an upgrade recently and they forgot to bring in some packages after that. I believe that's what I'm getting bit by. I think I'm going to have the same problem with this image, but I'm going to quickly test it just to find out. Yeah, all right, same thing. Let me try not passing that module quick just to see. This one, I can't remember if we made a version of it that used a new enough distro that didn't have the glibc incompatibility. Yeah, this one has that. That's the error that I was trying to describe. Well, I apologize. I'd forgotten that we had not fixed this issue since that last update. Let me at least explain sort of what's going on so that you can understand what's supposed to happen when it's working correctly. For MPI support, what we're doing here is we built that image with just a standard MPI installation with no options about the interconnect that might be on the Cray. And then what we do when we run the container image is we inject the host MPI into that container environment and then set some variables so that gets picked up by the application. So this means you can get like native performance and it'll take advantage of the interconnect, even if your application wasn't built, specifically to use that. And this works well. It just so happens we've hit this one, issue with an update where we forgot to fix something. So I apologize for that, but at least hopefully it gives you the idea of how it's supposed to work. If we built the Docker image did the MPI application build with a fairly recent OS, then you wouldn't see these issues. In fact, we might try it with one using the E4S one. We can circle back to this because Samir, in your E4S one, what's the base OS? Is it still 1804?
Ubuntu 1804
is still 1804.
Is one, okay. and also 2004 in another.
Okay.
So I can show both of those.
Yeah, the 2004 should work because that doesn't need the older glibc. Okay. Yeah. So
I can show that. Yeah.
Okay, great. All right, let me just one final thing that I wanted to show, and that is volume out. So in all these cases, most of what we're using is information that's already in the image. One concept that you see both in Docker and we have the same capability in the HPC runtimes is volume mounts. And so with volume mounts, what you can do is, and I'll use the Ubuntu 401 for demonstrating this. Yeah, let's just do that. You give it a path outside the container. So I'll do like my scratch directory. And then you give it a location that you want it inside the container. And so I can look in there, that's my scratch directory. What is useful about this is, and that's what the command looks like, is that means you can just create containers that can assume that data will be in certain locations. And even if you go to different systems, you can kind of abstract that and you just can use the volume mounts to place those pieces in the right location. And so these volume mounts are typically how you're going to handle your large input data as well as your output. Because you don't, in Shifter, it's a read-only mount, so you can't even write into other locations, even on if you were using Docker. So if we flip back over here, whoops. We're doing AWS, you can do the same concept here. I remember if we've got a temp data, for example. So same thing. The one thing to know about containers, especially when you're using a more standard runtime like Podman or Docker, is in most cases, if you write into a location, these things are ephemeral. So if I touch a file here, all right, I exit out and I come back in, I'm not going to see that file because it's created a new container for me. So these things are ephemeral. You usually use volume mounts as the place where you kind of put persistent data, both for access, for reading, and for writing typically. Yes, volume is similar to a bind in Singularity. Same thing. And so you will see different terminology in the different runtimes, but they generally will have similar concepts. All right, so that's the quick tour. I do apologize that I forgot to check this example and didn't realize that it wasn't working right now. I think they have an update ready for that, and hopefully it'll be in place during the next maintenance. So we should get that back. I'll try to come back into the documentation and maybe make some updates, just so if people want to revisit this and try it, they can. All right, that was it. If there's any other questions, we can fill those. Otherwise, I think we'll start with Samir's section, right?
Yeah, let's turn it over to Samir. Thanks, Shane.
So before I start with the E4S slides, I just wanted to answer Mark's question. You can download the custom.json file, and here is an image where PAPI is already installed in the image. So you can see that if I say PAPI avail, I'll see the counters from this Platinum CPU, and you can see which counters are available, like level 1 instruction cache misses, level 2 instruction cache misses, and all of these counters. So you are able to access the hardware performance counters from Docker. And
Okay,
if you go to the SRC, go ahead.
I was just going to ask, and the ones that report as interruptible, you really can get interrupts off of them?
That's a good question. I have only used it at the entry and exit level, not the interrupt level. But I think the full functionality of PAPI is available now when you try this. So if it doesn't work, please get in touch with the PAPI developers.
Okay, I would guess if you can get this far, the answer is probably yes. But the critical question is whether or not the event is derived. And as long as it's not derived, you're supposed to be able to interrupt off of it.
Okay.
I would assume so, right? Because you're interacting directly with the kernel at this point. Rather than
this is the custom
kernel that's virtualized, right? And some of those interrupts are secondarily driven.
Yeah, like I said, I've seen 20 talks on virtualization, and everybody assures me, oh yeah, you get full access just like you're running on the the real machine, and the answer is like always no. So pardon me for being skeptical.
I mean, keep in mind that this isn't virtualization though, right? You're kind of directly in the same kernel as these. The only times I've seen typically issues is where you have some library that's in the container that needs to interact with the device, and you can get mismatches in those. But you have a pretty much direct path to the device.
Okay, thank you.
You can try this example. I've put the commands in the chat window. And let me just go real quick through some of these slides. You can go through these later and ask us any questions. I would just like to say that as our software is getting more and more complex, it's getting harder to install our tools and libraries correctly in an integrated, interoperable software stack. And that's what E4S is trying to address. E4S is a curated SPAC-based distribution. It includes binary build caches for multiple architectures. You have container images that are full-featured or base images, and they are available on Docker Hub and E4S web page. We have recipes for creating your own custom images from base images, integration with GitLab. We have a validation test suite, and even a launcher tool called E4S that will help you replace the MPI in the application using MPitch ABI or even OpenMPI. We'll see this example. There are VirtualBox images, even images on cloud platforms. And starting with our first release in October 2018, where we had 24 products, now we have 100 full release products. And we use the SPAC package manager for the software delivery. And it provides us a very versatile package manager that allows us to specify the versions of the packages. And the reason we do this is because our software is getting really complex. This is the dependency graph of Nalu. This is the dependency graph of deal2. And you can see how deal2 depends on SLEPC, which depends on PETC, which depends on SuperLU-dist, Parmetis, etc. This is the R minor package. So you get the idea. We are getting really complex in our software, and even proprietary codes have a lot of these open source packages in blue that they depend on. And we are actually building an entire ecosystem of, say, 24 applications with 80 software packages with multiple architectures, compilers, programming models, versions, and that leads to a combinatorial explosion. It has gotten so bad that there are centers that are dedicating many FTEs just for building and porting of these applications, and they often trade reuse and reusability for performance. So we must make it easier to rely on other people's software. And it's typically not easy to install software on a supercomputer, where you typically install all the different packages that you need for your application. And then you just fight. You just fight with your configure scripts, your make files, tweak the arguments, and somehow you get all 16 packages built. And when you try to run the code, it can seg fault and you start all over again. So there has to be a better way to do this. And you may say, well, what about modules? Well, modules just set the path, LD library path, and man path, and other environment variables. The actual package has to be installed by someone else, someone likely at the supercomputing center. And so you can just use SPAC. And to do that, you just say git clone on the SPAC repo, source their setup and file, and then you can just install a package. You could say SPAC install tau, and it will install tau and its dependencies. I also recommend doing a SPAC compiler find, so it can find the compilers so that it doesn't have to install those from a scratch, or external find to get packages like M4, AutoConf, which may already be installed. And then you can just install a package like this, or say, please install tau version 2.31 with the compiler version 9.30, where @ symbol is used for the version, percentage is used for the compiler. So it understands compilers that it has found in the compiler find stage. You can specify build options like plus ROCm, you can say plus MPI, and even specify like use the MVAP pitch 2, which provides the MPI version 2.3 without the wrapper RPath. Wrapper RPath, tilde wrapper RPath, or without this argument is critical in replacing the MPI with an external MPI. And then you can see which packages are installed, and visit the spac.io webpage to learn more about it. I'm sure many of you may have already used it. Here is the base images. We have a minimal image for E4S, for x86-64 and PPC-64LE. And we have base images for NVIDIA GPUs, which includes x86, AR64 for ARM64, and Power 9 PPC-64LE. We have ROCm base image, Intel One API base image, even continuous integration images. This is our base image of Ubuntu 18.04. It has over 1 million downloads. It's been adopted by the Linux community. You can see the Singularity download, which has support for all 3 GPU architectures. Yes, that's right. They have packages like Cocos, which support all the 3 different GPU architectures within the same container image. And you can see which packages we have. There are 100 different products built with GCC. They have packages like Amrex, packages like GasNet. There is Cocos, MFEM, MPitch, and they have GPU runtimes. So you can see One API, HipCC, CUDA, HPC, all of these packages for different GPUs are already there in the Singularity full-featured image. This is for x86, so you can see PETC, PDT, Parsec, ParaView, Charliecloud, and we have 3D visualization tools like Visit, ParaView, Taos, Paraprof, all integrated in this image. So you can use GPUs, you can use TensorFlow, PyTorch for the different GPU architectures. You can even use Julia and Python. And this is for IBM, similar 100 packages. And these are the full featured packages. You can pull this image using the Docker pull command, and then you'll have it. Just go get a coffee because it may take a little while to download it. And here are the tags. This is the 22.02 February 2022 image that we have support for these architectures. And if you wanted to use this using Singularity at Oak Ridge systems, you can just say Singularity run with the --rockum, and then specify that don't use any environment variables except for display. So you can pass that along, and this is an image that's already downloaded in the ORNL systems. Here is a base image with Rockum, so you can have a base image on which you can build your own custom containers. Here is the same image in NERSC, and this is a bare metal install of E4S. And here is the Shifter image at NERSC, where there's a base image as well as a full featured image. The base image is much smaller. It just has GPU, runtime, and SPAC. So you can see that this is an image that I picked. This is the full featured image 2004. And I can access NVIDIA SMI on Perlmutter. I can see the SPAC packages, even see module avail commands. And you can see which packages have been compiled with CUDA architecture 80 or for A100. This is a spac.yaml file that you will find in the root directory, where you can take this file and tweak it. You could just say, I want to use a base image. I want to use this file, but I'm just going to use 5 packages. I don't want 100. And I'll just take the ones that I want and create your own custom smaller image. And then you can just, it's easier to delete from this thing which shows that all these 100 packages are installed and working than to start from a scratch sometimes. So you may want to use this to create your own images. There was a tutorial on Monday where they used the SuperLU dist and other packages that used the E4S full featured image to create their own custom image. Here is a build cache with over 80,000 binaries that can speed up your install of packages, whether it's in a container or a bare metal platform, and you don't need to install it from source code. You can just use this. This is the image that we will use for our hands-on session. I know we are running a little behind schedule. I'll just do this quickly. It has a number of packages. It has the full featured ECP image. We even have a VirtualBox image if you want to run this on your own laptop. And this is the tool that is used to launch MPI jobs. What this allows you to do is it allows you to replace the MPI in your containerized application with the system MPI. And this system MPI could be Intel MPI, MVAPICH2, OpenMPI, and you can replace it. And all you need to do is you need to specify which kind of container you're using. So it could be Docker, Shifter, Singularity. You could say, this is the image. And what do I need to do when I launch the image? What is the startup command where I can specify SPAC, load, Charliecloud, or something like that? And then I just say E4SCL MPI run, and it figures out MPI in your path, and it will just run it and substitute the MPI. It sounds too good to be true, but I will show that this actually works. Here is the architecture. E4S is a conduit for future leading edge HPC software targeting scalable next generation computing platforms. It has emerged as a new top level component in the DOE HPC community. It can provide better, faster, and cheaper software integration. Much of this work goes on at the Performance Research Lab at the University of Oregon. As travel opens up, we welcome you to come visit Eugene and work with us. I would like to thank our sponsors, DOE and other agencies and our industry partners, including AMD, AWS, IBM, Intel, NVIDIA, and our partners at other institutions. I would like to thank the Exascale Computing Project for their sponsorship. And to get started, you can reserve an AWS instance. It's the same page we are referring to. Log in like this using the web browser. You don't have to install anything and just start looking at the README file. Here is the image. You may have to press the space bar, press HPC Linux 12 exclamation as the password. And I've changed the prompt here. And I will just show you some examples. You can run SYCL on your Mac in an Ubuntu container, but I have not been able to see the Gen 9 embedded GPU, or maybe it's because I don't have an Intel GPU. I think I have I have an Intel GPU, but I have not been able to see that through Docker. I have been able to do that on a Tiger Lake platform, on a Tiger Lake Gen 11 CPU. But that is on a Linux laptop, and that's different. So here is an example, just taking off from where Shane left. In this containers directory, I have a Docker file. You can see I'm doing this. And then there's a README file here where you can just say cut and paste here, Docker build. Okay. I'm just going to say Docker build my hello MPI, and there it's done. Docker run. And then I can say my hello MPI latest. Let me just decrease this a little. Yeah. Okay. And there it is. I can go and look at app hello MPI run -np4 app hello. And there I have it. If I want to look at the same example, hello world.c, and run it in Singularity, what do I need to do? So in the README file, you'll see that we have examples with Singularity. Here is the hello world example. I'm going to try building it with hello.def. Okay, let me just move away the hello.sif file that may be already there in your directory, or delete it, and just say cat hello.def to see how you do this with Singularity. I'm using this ECP E4S Ubuntu image, which has MPI in it. Here is a full example of what this Singularity image format def file looks like. Here I'm saying this is copy this file over as hello world.c. You load up the SPAC environment, load the mpage, ls-l, see that the file is there, MPI-cc, generate this hello file, test it like this, and run script that just runs this when you launch the container. Someone was asking, how can I get MPI run to run as soon as I say, Singularity run hello.sif. So then to do this, all I have to do is say sudo and give the password like this. And then you will be able to do this. And it will just generate this image, a Singularity image, from your main def file. It will just create the image. It will be ready. It will test it. And you can see these commands for loading it. You just have to load the SPAC environment and then load mpage from this image, which already has mpage installed. And then you'll be able to just load this and run it in this manner. Now, while it's doing this, let me show you how I can use a full-featured image. Here is the ecp.simg. I can say Singularity run with ecp.simg. Okay, here I am now creating this container, and all I had to do was say Singularity run this image file that you can download from the E4S web page. This image file has Intel One API, it has ROCm, it has NVHPC and even CUDA all in one image, and 100 different packages that are pre-installed for you. So you may want to use PETC, HDF5, Trilinose, all from this image. And here is the Singularity prompt. You can say conda activate ROCm or CUDA, and then use the TensorFlow and PyTorch, or you can say SPAC find like this. And here I will go to an example called Zoltan. Okay, I will say clean.sh over here. So what did I do? I said Singularity run ecp.simg, and then I said cd to Zoltan directory, and then clean.sh and compile.sh. This image is big, over 40 GB in size, because it has each of those container, each of those vendor runtimes, which can take over 10 gigs in size. But it has everything you may want to use. And if it's a 40-50 GB image, you can get everything in one particular place. So here I can say compile.sh. Okay, this will compile the application. And now my application is ready. It was compiled using MPIG from this image. Okay, and this is using SPAC's installed MPIG and a whole bunch of these libraries. These libraries come from the Trilinose. Okay, so now I'm going to exit from this image like this. And okay, here hello.sif is ready. To run this, you just do the same thing, Singularity run hello.sif. And this echo comes out. This is what happens when you run the container, and it runs this on 4 MPI ranks. Just like our image def file said it would. So here is the hello.def. And this is what happens when you run the container. And here is the SPAC loading and MPI run command, which is what happened when you did this. So you can create a simple application with this. Now here, I have created this application with Zoltan. Here is the binary, but I'm not going to run it inside the container. I'm going to exit right out over here. And I'll say LDD Zoltan. And it's not a regular file. Sorry, I'm in the directory. You can see that the libraries that I wanted are there in the container. They are not found on the host. Okay, I want to even look at this glibc issue, but I want to use the container, the ecp.simg, and extract the Trilinose libraries from there. So Aztec OO comes in, but I want to use the system MPI. So I may have run E4SCL with one API, Intel MPI.sh. So let's look at this. I'm going to try and replace the MPI in the container, in the binary, with the Intel MPI. And here is the image. Here is the Singularity. And then this is the startup script. So if I say source.sh, it just says load up the SPAC, load up the Trilinose, and you're good to go. With just these three things, I can use the E4SCL Intel MPI.sh. Without modifying the binary, I'm going to switch from MPIG to using OpenMPI, using the Intel MPI over here. And how do I know if we are using that correctly? You can see sometimes some messages that come from the warning messages from the MPI implementation. And that tells you that it's coming from this one API. I also have a which MPI run And it will do the job of finding the libraries that it needs to substitute for you. It will do that for you, and it will take care of it. We also have here it found 15 libraries that you don't have to worry about mounting in the image. It will take care of it for you, and it will just run it with this one MPI run. We also have OpenMPI, and it uses the Y4MPI package from CEA in France. And then we have MVAP-H2, all 3 MPI versions that are different from MPICH, but you can load this, and this E4SCL tool will do this for you. It's also installed on the Oak Ridge National Lab systems. It is installed on the ALCF systems and also in Cori and Perlmutter at NERSC. So you can replace the MPI more easily, even when you're using Shifter or Singularity, and just specify which image to use, what is the startup command, and it will take care of finding the libraries, and it will run. This is the application running on that image. If I try to run this E4SCL with OpenMPI, I just use this Y4MPI like this and say from MPICH to OpenMPI. And let me just run this to show you that with the same binary, I can replace not just the MPI in Trilinos with the OpenMPI, with the Intel MPI, we can also replace it with OpenMPI. No, actually, Belen, this case is showing you OpenMPI, which does not have the MPICH ABI at all. It is going to use this Y4MPIs, and here it's running the same image. It's running the application with OpenMPI. And here is similarly for run E4SCL MVAP-H2X. MVAP-H2X provides it access to the AWS Elastic Fabric Adapter, EFA. You can see some message from MVAP-H2X saying that, hey, you can get even better performance if you use libxpmem.so. Here it found 19 libraries to substitute. It'll take care of it, and you will be able to run the same binary with the same container image on 3 different MPIs. So we do not need to specify any of these MPI fabrics. And there it is, MVAP-H2 running as well. So you can try this example yourself. You can see CD to your Zoltan directory. Like I said, Singularity, run, ecp.simg, clean.sh, compile.sh. And then more importantly, you need to exit. And then say exit, come back to the host, and then say run E4S CL and say openmpi.sh, for example. So here I've covered how to run and substitute the MPI with something else. I've covered how to use a Singularity image starting from a Docker image. And I hope you can create your own examples with this. Try this with the full Trilinos application and let us know how we can help you. With this, I'll hand over back to Shane.
Right, thanks. Since we're short on time, we're going to skip the best practices, but the link to the slides are in the GitHub site. So, feel free to read through those and take a look. I think there's some good tips. A lot of these are sort of general practices for both building images as well as running them on HPC systems. I wanted to try to redeem myself just a bit. I fixed the documentation, the site, and I found an image that the image I was testing with was actually slightly different from the one that we were building. So I just wanted to quickly show that before we wrap up. So the documentation now references this image. Wait for it to start up. And in this case, this is using the Ubuntu 18.04, which actually does have a new enough libc. I think the version I was actually trying to test with was one from a long time ago that used Ubuntu 14, which was why it needed that other flag. So in this case, we don't have to pass that other module command. You can just do Shifter by itself, and this should hopefully work. Okay, so if you reload your page and try that exercise should work now. One thing I wanted to point out is how we're doing, and Charliecloud asked a question about ABI compatibility. For this example, that is how we're doing it. So here I'm back on the AWS host. I'm gonna pop into that same image. I'm gonna do an LDD on the app hello, and you'll see that it's using, the MPI it's using is use your local bin. So it's in the image in this case, right? So when I do that, it's using an MPI that's compiled into the image. Now, if I contrast that and go on to Shifter into the image and do the same thing, you'll notice that now the MPI it's picking up is opt-UDI images, So this is the MPI that's coming from Cray with the Cray system, and that's being injected in and being picked up by the application. So this is how we can kind of have portability and sort of native performance. Most of the runtimes are doing similar kind of tricks. You can compile the MPI into your application. I mean, compile in the specific one and not use this approach, but it might not be as portable. So anyway, I did want to quickly explain that. Again, go through the best practices on your own. And the other thing I would mention is there is a link in the, one is continue to ask questions in the Google Doc, and we can answer those for the next, throughout the day if you have any questions. The other thing is, I think, did we have a link to the Slack link in here, Andrew? Yes, there it is.
I will make sure it's in the chat as well. And just
yeah. So there's an open invitation to a Slack team for containers in HPC. It's got a lot of people in it. I'd highly recommend, if this is something you're going to work in and you want access to people with, experience, it's a great place to go and ask questions. And so if you do have any questions about both this, the other slides that we didn't get a chance to go through, or Samir's contents, that's a great place to go and continue the discussion. Andrew, any other things we want to do before we close out? We're a minute over now.
Yeah, I was going to say we're about at time, so I think we can stay on if there are any remaining questions, but we should probably let folks go and enjoy their afternoon or evening at this point, perhaps. So just wanted to say thanks everybody for joining us. There's plenty more materials here we can share with you as well. The other thing I'll probably try to put in the chat right now is a link to our SC21 tutorial as well, which is a full day of more containers. So yeah, there's plenty more to build from. This is meant to be sort of a sneak peek or a quick intro. So with that, I think we'll conclude. And if folks just have any remaining questions, we can stick around for a couple minutes. But thank you very much for joining us.
We'll keep the instances running for a few minutes, maybe 10, 15 minutes, and then we'll bring them down. If you want to get an instance for your exclusive use, please reach out to us and we'll be able to boot it on demand for you so you can carry out these hands-on sessions later.
All right.
Well, thank you, Balint. I'm glad you found this tutorial useful.
Thanks, everyone.
Thanks.
Samir, thank you for response about 3 months gap between versions of ROCm and E4S container.
Yes,
yeah,
and we'll have a new version
enough,
released at the end of this month.
Yeah, but that should be enough. Like 3 months is okay for data centers. Thank you.
Okay, thanks.
Bye.
Bye.